These are the formulas that you were learning. This is the charge, this is the force, Coulomb's law. This is the electric field, which is force per unit charge. This is the electric field for the point charge. This is the flux, and it is related to the Gauss law. Gauss law is there, this total charge enclosed divided by the relative permittivity of free space. Then you have electric field, which is related to the potential. Then you have potential, which is work done per unit charge, and it is, if it is between 2 points, the potential difference, work done per unit charge. Electric potential due to point charge, and the electric static potential energy between 2 point charges represented by, and if you have many charges, you can add the energy like this. So you can add the sum of forces on different charges is F12 plus F21, and these the, and similarly you can add the total electric field E1, E2, E3, and this is known as the superposition principle. Okay, then we have the capacitor. So capacitor, the charge stored in a capacitor is CV. Okay, then the energy stored in a capacitor is 1 half CV squared, and the capacitance of a parallel plate capacitor is represented by epsilon naught A over D, I think. So this is the capacitance of a parallel plate capacitor. Then then you have, please mute yourself. Hello. Okay, then you can add capacitors into series or parallel. So series like this, and in series you can add the equivalent capacitor like this, C1 plus C2 plus C3, and then in parallel the capacitor would be like this combination, and you can add equivalent capacitor C1, C2, C3, and so on and so forth. And then you have current. If your current is Q times T, okay, Q over T, charge flow, and you can write it like this, dq over dt. Then you have related to the current, you have the drift velocity, which is I over N E, I think A. Okay. Then you have magnetic field, and the force of the magnetic field is Q V cross B, and you can write V is VB sine of theta. This is the force on a charged particle. Then you have force on a conductor, I L cross B, which is I L B sine of theta. Then you have magnetic field, which is Ampere's law, B dot dl, closed loop integral, mu naught I. And if you place a coil, or then or a rectangular loop, it experiences a torque, which is N I A B sine of theta. And the last thing is magnetic field due to due to uh, solenoid, which is mu naught n over L I, and the solenoid is like this shape. So you can apply the most important equations in this is this Ampere's law, this Gauss law, and this Coulomb's law. So the goal is to find the force between the charges, but we find the force using the electric field. Electric field can be finded out by the potential, and the potential can be written in terms of the energy, which is a scalar quantity, and Rest goes like this. So the goal of this course is to calculate the forces between the charges. So we move on to calculate the force through electric field, then move to the potential, then move to the energy, because we're going to solve the problem by dealing the scalars, which are easy to solve. So let's start by solving questions. Okay, these are some of the formulas that you will be needed in solving this exam. So a metal sphere is initially uncharged. After being touched by the charge rod, the metal sphere is positively charged. Then, strictly speaking, how does the mass of the sphere changes? So, a metal sphere is initially uncharged. After being touched by a rod, the metal is positively charged. It means you do a charge by rubbing it or touching it. Okay. So when an uncharged metal is touched with the charge rod and become positively charged, it means that the sphere has lost electrons. So it lost electron. So sphere has lost electron. It means it's because mass of the electron, which is very small, but it has a mass 9.1 10 to the minus 31 kilogram. So it loses that one electron mass or many electron more. So it mass going to be decreased. So the mass of the sphere becomes smaller than before it was charged. So the mass of the sphere becomes smaller than before it was charged. So its mass got to reduce. Next question is, two charged particles attract each other with a force F acting on it. If the charge of the particle is doubled and the distance separating them is also doubled, so the force acting on it of the two particle has. So now we apply Coulomb's law, Q1, Q2 over R square. Now both the charge is going to be doubled, both the charge is going to be doubled, and the distance also got doubled. So how to do this? This is 2Q1, it will become 2Q1, and this will become 2Q2. Both the charges got doubled, and the distance got doubled as well. And it could be quadruple or triple or any number. So just do like this. So 2 times 2, which has become 4. So 4 q1 q2, and this square will become 4 r square, and this 4 and this 4 will be cancelled out. So the prime force, when we change, we double the uh, charges and double the distance, you will get the same force, which is F. So by changing or by doubling the charges, both of the charges, and double the distance between them, remains the force same. Okay. So if either two of them is doubled, for example, if the charge Q1 is doubled and Q2 remains the same, then, or if it is doubled, the distance is doubled, then force got halved because it, well, this, and vice versa for many different situations. You can check with this. If it one double and the other double, and if the distance reduces to half, it the force got increased because they are directly proportional and this is inversely proportional. If the charges increases, force increases. If the charges go down, if the distance between the charges increases, the force go down. Okay. Next question. Two identical negative charges are located on the axis symmetry with respect to the origin. What is the direction of the electric field created by these two charges at point P? Y axis above the origin. So you know that the electric field lines originate from positive charge and terminate to negative charge. So if these two positive charge, so at this point, What will be the direction of the electric field? Will be like this. For this charge, this is also negative. What will be the electric field direction? Is in this direction. So what is the total electric field? The total electric field will be the combined effect of this will be in this direction. So it is in the negative y direction. So the answer will be negative y direction. So its direction will be in this direction. So the electric field will be, because this is positive, this is negative. So its direction is in this direction. So it's negative y direction. Now, question number 4. The two irregular objects A and B carry charges opposite sign. The figure shows the electric field lines near each of these objects, where the electric field is stronger, closer to A or closer to B. So, where the density of the charges increases, density of the field lines increases, which means the charge is stronger. So if the density of the charges increases, the charge is stronger to that particular thing. So the field lines is closer and dense with respect to A as compared to B. They are separated. So electric field is closer or stronger to closer A. Okay? Because if you have a charge like 3Q and Q, the field lines are more dense due to its magnitude, and field lines are less dense. And this tells you about the magnitude of the charges as well. Okay, next question number 5. A charge of 200 microcoulomb 200 microcoulomb is at the center of a cube edges 95 centimeter. No other charges are nearby. Use the Gauss law to find the flux through each face of the cube. Each face of the cube. So you have a cube like this. Okay. This is a cube. Okay. So at the center of the cube, there is a charge which is Q, that 200 microcoulomb. And the edges of the cube is 90 centimeter long. So edges is this 90 centimeter long, and there is no other charge in the nearby. Then we use Gauss law. So Gauss law says that phi of electric flux is Q enclosed divided by the epsilon naught. This is the Gauss law. So Q enclosed is what? 200 microcoulomb. Micro means 10 raised to power minus 6. And epsilon is a relative permittivity of free space, which is 8.85, 10 raised to power minus 12. So you will get the flux, which is 2.26 10 to the 7 Newton meter square per coulomb. Okay. Okay. So this is the flux, but this is a flux for one surface or one oh, each cube face. So each cube has 6 faces: one, two, three, 4, 5, and 6. So you have to divide it by 6 faces. If it is a square, okay, so it has only this is a surface, then 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 this is a surface. So it has 6 faces, and the flux is passing to every face. So the total flux at each face will be, this is the total flux through all the faces, and to each face you need to divide this flux. How many faces you have? 6. Then you divide this so you will get 3.77 10 to the 6 Newton meter square per coulomb. So you have both of the answer, but you need to be careful choosing the option. So this is the correct option. Okay, move to the next question. If a charge is uniformly distributed on the surface of an infinitely long cylinder with linear charge density lambda at location, at which location the electric field is zero, uniformly charged, this is on the surface. That is the important point. And if this is the case on the surface, it means it's a metal. So you have a situation like this. You have a cylinder, infinitely long, and all the charge resides on its surface. So there is no charge inside. So when there is no charge inside, it means the electric field inside is zero. Okay? Because if we apply the Gauss law says that E dot dA equals to Q enclosed divided by the epsilon naught. So there is no charge. Charge is zero, which means this integral is zero. How can this integral be zero if there is no electric field? So at which point, at which location the electric field is zero? So electric field anywhere inside the cylinder for any value of lambda, because lambda is the surface linear charge density. So lambda is the charge per unit length, which is on the surface only. So inside there is no charge, which means the electric field inside is zero at every location. At every location inside, the electric field is zero because there is no charge. And there is a general property for the metal. If it's a sphere or a cylinder or any configuration, for a metal, the charge is always resides on its surface. There is no charge inside the metal surface, and since there is no electric field inside as well. This is a surface. If we are talking about sphere, which is filled like a hard ball, which is filled, then there is charge is not equals to zero. If it is a surface or then it is hollow sphere, then hollow means which is empty inside. So then the charge is zero and electric field is zero. But if this is a sphere which is filled, it's a three-dimensional object, then the charge is not zero. So be in mind while reading the question what is given to you. Okay, next 3-point charges Q1, Q2, and Q3 are located at the corner of equilateral triangle. So equilateral triangle has all the sides are equal. Sides is this. So these three sides as shown in the figure. What is the total potential energy of the system of three charges? Now, to calculate the potential energy, so potential energy between the 2-point charges is just like this: K, Qi, Qj over R squared. Okay, then, so first we calculate the electric potential energy for Q1, Q2,
Lecture R
then,
not square.
sorry,
R not square.
oh no, R, sorry, that's a good point. R, only R, yeah. So this first we calculate the Q1 and Q2 energy, then Q2, Q3 energy, then Q2, Q3 energy, and we will get the total energy. So your total energy will be like U12 plus U13 and then U23. So your total energy will be Q1 Q2 over D plus Q1 Q3 over D plus Q2 over Q3 over D. Okay, D. So when we substitute the values, we have everything. Nano, this N is 10 raised to power minus 9. And we substitute the value of D is centimeter. So whenever you write centimeter, you do like this in meters. Okay. When we substitute the value, you will get the total energy, which is negative 1 microjoules. So the correct option is this. Okay. So next is question number 8. Figure below shows several equipotential lines. Equipotential lines means they have all the same potential, on the same potential. So if you are on that point, the potential across each sphere is the same. The potential across each sphere at every point is the same. The potential across on that surface is the same. So these are equipotential surfaces. Okay. What is the work done? The external work done to move a point charge Q from point A to point C. So we want a charge to move point A to C. So if you see this, if it's starting from 0, this is the point. So what is the potential at point 2? This 2, 0, 2, 4, 6, 8, and this is giving you the potential. So at point C, the potential is like this, which is in between 2 and 4. I think it's 3. And the potential is at 9 or at 8. At A is 9. So, okay. So how do we calculate the work done? So work done, external work done is calculated by Q delta V. So what is delta V? So delta V is nothing but VC minus VA. The second point minus the first point. So charge is given 2 nanocoulomb and the potential at point C is 3 volt and the potential at point A is 9 volt. So Q is 2 into 10 raised to power minus 9 and the potential at C is 3 minus 6. So you will get 12 into 10 raised to power minus 12 because 6 minus 3 is minus 9. Sorry, 9 minus 3 is 6 and 6 multiplied by 2 is 12, which is 9.
Hamza,
Yes.
how did you assume it was 3 and 6 and
Sorry.
not 8? How did you assume it was 3 and 6 but
Okay.
not 8 and
So
2?
so if you see this, this is a starting point. The potential is 0. Okay. So if you see this, the potential, it lies between the point C lies between 2 and 4. So it's 3. And similarly, 8 is there and you increase the potential over here is between the 8, 9, 8 and 10. This is 10. So it is in between the, so the potential over here is 9. So that's how we identify the potential and its starting potential at point B is 0 and either you can find A B B C C A, either any point the work done to calculate the charge or external work done can be calculated like this. Okay, so this is the work done, 12 nano joule. So this is the work done from the point A to C without changing its kinetic energy because these are equipotential surfaces. Okay, let's move to question number 9. So question number 9, a sphere of center C and radius r 3 centimeter has a total charge q 500 nano coulomb. A point P is located at a distance r 6 centimeter from the sphere center. Calculate the potential difference. The potential is zero at infinity. That is what we learned. So, what is the situation? Situation is like you have a conducting sphere which has a radius r, small r, capital R. Capital R is 3 centimeter, and it has a charge because it's a conducting sphere. Sphere is a three-dimensional object. So the total charge is 5 nanocoulomb. At point P, this is a point P, which is the R distance from the sphere, and it is 6 centimeter from the center. From the center, and this is 3 centimeter from the center. So calculate the potential P and calculate the potential at C. So this is the potential P and this is the point C. Okay. So we will calculate the potential at R, which is K E Q over R, and we will calculate the potential K Q over R. And then we will take a difference. So the potential at point P and the potential at point C. So K is nothing but 9 into 10 to the power 9. Charge is same, 5 into 10 to the power minus 9 coulomb over the distance. So if we are talking at point P, this is our distance. Okay. Oh, this is the center and this is the point P. Sorry, this is the point P. So the distance from center to point P is 6 centimeter, which can be write like this. So you calculate the potential at point P is 750 volt. And similarly, you can calculate the potential at a center, point C, just substitute the same value, but the distance would be 3 centimeter. And you will get the potential 500 volt. So what is Vp minus Vc? So 750 minus 1500. So you will get negative 750 volt. So the potential is okay. So a parallel plate capacitor. Question number 10. A parallel plate capacitor is connected to a battery. What happens to the stored charge? Stored charge Q if the plate separation is divided by 2 while the capacitor remains connected to the battery. It means we are increasing the distance. We are decreasing is divided by 2. If the plate separation is divided by 2, it means we are decreasing the distance. Okay. So if you have a parallel plate capacitor like this, its capacitance C is depends upon only the geometry. Geometry means it depends upon relative permittivity of free space between the plates, the area of the plate, and the separation of the plate, which is D. So it means we are decreasing decreasing the capacitance. So which means epsilon naught A, D is divided by 2. So this will go up. So this is C prime. So C prime will be 2 times epsilon naught A over D. And this is your C. So C prime is 2 times C, which means its capacitance goes on increase because they are inversely proportional. So what he's asking, the total charge stored. So the charge stored is related to the capacitance is Q is equals to CV. So if the capacitance increases by 2, the charge will also increases by 2 because they are directly related to each other. Okay. So so its charge going to be double because it the capacitance increases by 2. If we increases the area or decreases the area by 2, for example, if we decreases the area by 2, then capacitance go down by 2, then it will be half divided by 2. Okay. Now the question is 12. No, question 11. So question 11 is two unequal capacitors. Two unequal capacitors uncharged, initially uncharged, are connected in parallel across the battery. Which of the following is statement is true? So the capacitor is connected to the parallel. This is the parallel combination. You need to remember that the voltage remains the same in the parallel combination. So the voltage remains the same. Okay. So, and we know that the charge is related to CV and C equivalent. So, if they are in parallel, so C equivalent, need to calculate the C equivalent. So, the voltage is remains the same. So, what happened to the capacitance will relate it to the charge. Okay. So, the capacitor, which is the smallest capacitance, has the greatest charge. No, because they are related to each other. If the capacitance goes in increasing, charge will also increasing. So that is not the correct option. The largest voltage appears across the largest capacitor. Voltage remains the same. So this is not the option as well. The largest voltage appear across the smallest capacitance. That is not correct as well. So we left with one option. The capacitor with the largest capacitance has the greatest charge. So largest capacitance has the largest charge. Okay. So this option is correct for you. Okay. Now moving towards the question number 12. The three parallel plate capacitor with vacuum between the plates of each capacitor is connected to the C1, C2, and C3. So three parallel plate capacitor are connected as shown in the figure. So this is figure A. The battery has unknown. So you don't know the battery by constant potential. They have the constant potential in figure A. The total energy stored in the three capacitor is this. This is energy given in this A. Keeping the capacitor connected to the battery, a dielectric constant K is inserted to fill the space between the plates. C1. What is the new electrical energy stored in three capacitors? So if you see any circuit diagram like this, the first thing is to calculate, to solve this circuit, is to calculate the total capacitance of this circuit. Okay, so in figure A, first we calculate the total capacitance. So how do we calculate the total capacitance? So if you see this, These two capacitors, these two capacitors are in series, and this capacitor is in parallel to this. So first we're going to add C1 and C2 in series, and then add to the parallel capacitor with C1, and then you will calculate the energy. And the energy will be calculated by this formula: C equivalent V square. C equivalent means the total capacitance. So how to calculate the capacitance in series is like this: Ceq is 1 over C1 plus 1 over C2. So when you put the value of C1 and C2, you will get 4 microfarad. And then your circuit will be like this. This is the this is CEQ. Then it's become CEQ or 1 2. 1 2 is better because we are getting 1 2. And then you have another capacitor which is C3, and then it is connected to the battery like this. Now these two capacitors are in parallel, so you will add capacitance equivalent for figure A is C12 plus C3, and your total capacitance will be 8 microfarad. Now the total energy of figure A is given, which is 64 microjoules. So the energy in figure A is given, which is nothing but CEQA, the potential difference. And this potential difference is unknown. We don't know right now. So we need to find that unknown, because we know that CA, which is this, and we know UA, which is 64. So we can calculate it by, you have 64 micro means 10 raised to the power minus 6 joule, 1 half 8 microfarad means 10 raised to the minus 6 farad, and delta V squared. Yeah, delta V squared is remains the same. So when we calculate delta V squared, it will give you 16, and delta V is nothing but 4 volt. So now we have found this unknown. But the question is that if the circuit is changes to this, and then there is a dielectric medium inserted in the charge in the capacitor, then what will be the new electrical energy of these three capacitors? So now we're going to do the calculations for figure B. So figure B. So figure B is, so first these two are in series, but you have a dielectric medium. So the capacitance for this C1 will be changed, which is K C1, and the K is given by 2. So it increases by 2. So C1 is 12, I think 6. 6. So your C1 will become 12 microfarad. Now these two are in series. So we have calculated like this. So your equivalent capacitance will be 1 over C1, 1 over C1 prime plus 1 over C2. And when you do the calculation, you will calculate microfarad. Then the circuit will become like this, and then it will be parallel. This is 1 2 1 2, and then equivalent capacitor will be C12 plus C3, and you will get it 10 microfarad. Now we have known that we have calculated that the potential or the potential difference of the battery. So the energy stored in the figure B due to this dielectric constant is C equivalent times delta V squared. So 1 half 10 into 10 to the power minus 6 microfarad. Then you have potential, which is 4 volts squared. And when you do the calculations, you will get 80 microjoules. So if you see this, the the initial energy was 64 joules without the dielectric constant. And now the energy is 80 joules with the dielectric constant, which means that dielectric increases the capacitance. Dielectric increases the capacitance. So it increases the energy stored in it. So if you insert any dielectric medium, there is a constant for dielectric medium, then you increases its capacitance, which increases its energy, and you and because it is related to CV, so it stored more charge. So charge which also increases because capacitance increases, charge will increases. Now question number 13. Now the electrostatics gone. Now from here onward, we're going to work on electrodynamics. When the charges are moving, when the charge move, it produces current. Okay, and current produces the magnetic field. So from question now onward, we are entering into the electrodynamics and constant magnetic field questions. So uh, uh, a 4 ampere current runs through the gold wire. Gold wire is a metal wire, and metal has a property, it conducts electron due to free electrons. So the radius of the wire is 0.5 millimeter. Gold has this free electrons per cubic meter. Then what is the drift velocity of the electron? So it's the situation is like this. You have a gold wire like this, and the radius is 0.50 millimeter, and milli is a prefix which is 10 to the power minus 3. Okay, so what is the drift velocity? So current, and it is connected to the battery, and when the current flow, the electron starts to move in a particular direction, so they drift. So the current is equals to the number of electrons, the charge of the electron, the velocity of drift electron, and the area of the wire. So what we wanted to find is VD. So VD is equals to I over N E N E A. So we have number of electrons, we have the charge of the electron, which is 1.6 10 raised to the power minus 19 coulomb, and the area. So the area of this wire can be, because it's a circular area, so the area is pi r square. Mostly in your exam, the symmetry is circular. So be remember that formula, because in many cases, the area is just like this. Unless you have a rectangular thing, okay, the area of rectangular thing is length multiplied by width. Mostly the case is for the wire, and the area of the wire is calculated by this if you are given by the radius r. So when we calculate this area, it will be 0.785 10 to the minus 6 meter squared. And when we substitute this value, we have N over here, we have E, which is given in the constants, and we have area over there, and you have a current I, which is 4. So the velocity you will get is 0.00054 meter per second. So this is what you get in meter per second. But the answer is all in millimeter per second. So how to convert meter per second into millimeter per second? You just multiply it with the number 1000. So this will be millimeter per second. So when you multiply it with the 1000, you will get the velocity in millimeter, which is 0.54 millimeter per second. So the correct option is, I think, this. Okay. Now, the next question is related to cylindrical wire. So if you see, this wire is a wire as well. Okay. So you have a cylindrical wire. Mostly the situation of the wire is like this: resistance R and resistivity rho. If the length and the diameter are both cut in half, what will be its new resistance? So the formula for the resistance of a wire is rho, which is resistivity, the length of the wire, and the area of the wire. Okay. So now R. So what is going to do? Both the length and the diameter. So I told you that this is a wire and the area of the wire is like this. So area is pi r square, and r is radius, which is related to the diameter by this. So what we are going, we are substituting d square by 2, d square by 4, sorry. So this is the area. What we are going to do is diameter cut into half. So we substitute the diameter to the half divided by 4. So what you will get, 8, 4, 4, and you will get pi d square, 4 multiplied by 4, this will become 16. So this is your area. This is your area. Now resistance is rho, rho. L is also going to be half, and the area is pi d square by 16. Okay. So if we write, this formula is pi L over pi d square by 4. So this 2 and this 8. So rho L over pi d square over 8. So here is 4 and here is 8. So we can write it as rho L pi d square 2 multiplied by 4, and when rho L over pi d square over 4, and this 2 will go up, and this is the same resistance we have. Now this is R. So when you cut the length and the diameter of any length of the wire is half and the diameter is half, it means you have increased its resistance 2 times. So this is the correct option. Okay, now moving towards the circuits. So question number 15. When the switch is open, when the switch is open like this, This is the open situation. And when it is connected, it's closed. Battery reads 4.2 volt. When the switch is closed, the voltmeter reading drops to 4.10. So this is your EMF, this is your terminal potential, and the ammeter, this is your current I. Find the EMF, the internal resistance, and the battery circuit R, resistance R. Assume that 2 meters are ideal. It means they don't lost the energy or the current, so they don't affect the circuit. So what is the formula? So formula is V terminal is equals to the EMF minus the I and the R. And this R is small r is the internal resistance of the battery. Internal resistance of the battery. Okay. So we have V terminal, which is this. We have EMF and we have a current. So we can find out R, which is nothing but EMF minus Vt divided by I. So we have all the values. And when we calculate the internal resistance of the battery when the switch is closed, so the internal resistance is 0.050 ohm. This is the internal resistance R of the battery. Now, what is the find the EMF, the internal resistance of R and the circuit resistance. So how do we find the circuit resistance? Circuit resistance is using the Ohm's law. So V terminal is I R. So R is V terminal over I. So V terminal is 4.10 and I is given 3 ampere. So we get 1.37 ohm. So this is our resistance. This is our EMF and this is our internal resistance. So 4.2 is your EMF, 0.05 is your internal resistance, and the circuit resistance is 1.37. So this is the correct option. Okay, now move to the next question. The three identical light bulbs having the same resistance and the same power rate are connected to the same battery in two different ways, figure A and figure B. So in figure A, all are connected in series, and in figure B, this and this are connected in parallel, and then this is connected to series. So what is he wanted us to calculate gives greater total light. Which connection gives the greater total light brightness? And the brightness is related to the power. So power of any circuit is I square R or IV or V square over R. Either way you can write the power. So for the circuit A, the resistance are connected in series. So these are the resistance. So we represent it as R bulb or R anything. So you have three resistance. So your total resistance R EQ in series resistance is added like R1 plus R2 plus R3. And be remember that it is contrast to the capacitor. In parallel, we added capacitor like this. But in resistance, we added the resistance in series like this. Has to be remembered. So the total resistance should be 3R B R bulb. So what is the power? So what is the current first in each of this? Because they are in series, so the current will remain same. So each across each bulb, the current will pass as the same, which is nothing but the voltage divided by the total resistance, Ohm's law. So the total resistance is 3R bulb. So this is the current. Now what is power? Power is I square R. So power is IA square and R total. So now we have IA, which is epsilon or EMF, and divided by 3R bulb square multiply by R required, which is R bulb. So we will get total power is E square 9 R bulb. Okay, so this is for the figure 1. Now this is for all for figure 1. Now for the figure 2 or figure B, so these two are in parallel. So we need to add the resistance in parallel. It will be like this: R12, R1 plus 1 over R2. It will be 2 over R bulb. So the total resistance for these two, which is in parallel, is R bulb divided by 2, because we take the reciprocal. Now this two resistance, the combined effect is this: they are connected to this is with series, so we add the series. So total resistance in the case of B is equals to R12 plus R3 or R bulb. So you will get R bulb over 2 plus R bulb. So your total resistance required for the circuit B is 3R 6 over 2. So what is the power now? So this is the current resistance. So what is the current in the circuit B is R equivalent B, which is nothing but E over 3 by 2 R bulb. These are R bulb. So the current in the B circuit is 2 epsilon naught 3 R bulb. So this is the current. Now the power is IB into R bulb. So IB is 2 epsilon 3 R bulb squared into R bulb. So see, this is 4 epsilon square 9 R bulb squared. This one and this one will cancel out. And if you see the expression for A and see the expression for B, so power B is 4 times power A. So which has a brightness, strongest brightness, the connection B. Okay, now next circuit is this. So you have resistance, these are in parallel, and this is in series, and then this is connected to parallel. So first we will calculate our 1 2 1 2 are in parallel, so we add resistance like parallel in R1 plus R2 like this, and this will be like 1 over 3 plus 1 over 6, which is 2 plus 1 over 6 is equals to 3 by 6. So R12 is 2 ohms. Similarly, then your circuit will transform like this. So you added these two resistance, it will become 1. Then it is connected to this series. Then it is connected to this in a parallel and with the battery A and B. So this is R4. This will become R12 and this is will become R3. So these two are in series. So you just add R123 is R12 plus R3. So just substitute the value. You will get 10 ohm R123. Now your circuit will transform like this. So you added these two resistance, the combined effect will be one resistance, and then it is parallel to another resistance, and then they are connected to A and B. So this is your resistance R123 and this is your R4. So the total resistance, which is the equivalent resistance, is R123 plus R4. So this is 10 ohm plus R4 is 12. No, no, no. They are in parallel. So they are in parallel. So how to add resistance in parallel is 1 over R equivalent is 1 over R 1, 2, 3 plus 1 over R4. Then you will have total resistance calculated like this 1 over R 1, 2, 3 is 10 and it's 1 over 12, and when you solve this circuit you will get R equivalent is 60 divided by 11, which is 5.45 ohm. So this is the total resistance. So this is how you solve the circuit. You can have many resistance, see them, which can you be solved. So this we solve first, then with this, and then with this, and follow the procedure. Okay, next question is another circuit. So in figure R1, R2, R3, the battery has negligible internal resistance. So we ignore the internal resistance. The current I2 through circuit is 4 ampere. What is the current in resistance 1 with R1? So if you see this diagram, this R1 and R2 are in parallel. In parallel, which things remains the same? Voltage. So the voltage across these two will be the same. So what is voltage? V is equals to I R. So voltage across R1, V1, and voltage across R2 will be the same. So voltage V1 is equals to V2. So I1 R1 equals to I2 R2. So your I1, the current through resistance 1 is I2 R2 over R1, and we have the values of all the resistance and the current in the second resistance. Second resistance has a current 4 ampere. So when we substitute the value, you will get the current in the first resistance, which is 12 ampere. Now, what is the total current? Oh, this is 8 ampere. So the total current in this combination, which has the same potential, is I1 plus I2 is equals to 12 ampere. Then what is the current is gone through the resistance, the EMF of the battery. So we have calculated. Now we calculated what is the EMF of the battery. So we need to calculate it. For that purpose, we need to calculate the total resistance of that circuit. So if you remember the past question, these two are in parallel and then they are connected to this with the series. So these two are in parallel. So R12 is R1 plus R2 is equals to. So when you calculate these two resistance which are in parallel, so your R12 will become 2 ohm, and then your circuit will be like this. It will become one resistance, then this resistance, and then this is your battery, which is EMF. Now this is R12 and this is R3. Now if you see this, they are junction to junction, which is in the series. So total resistance is R12 plus R3 is 7 ohm. So this is the total resistance. So how to get the potential with the total resistance? So you will get the EMF, EV or Ohm's law, the total current, the total resistance, the total current is 12 and the total resistance is 7 ohm. We will get 84 volt. So the current in the resistance is I1. You calculated 8 ampere and the voltage across the battery EMF is 84 volt. So this is the correct option. Okay, so this is a very lengthy question. We will come back to this question if we find some time, or I will upload the video for that as well. Now move to some easier questions quickly because we have left 15 minutes for the session. So this is the circuit you are given. The circuit below is used to charge and discharge a capacitor C. To charge the capacitor S1 is closed to S2 is open. The charging time constant is T1. To discharge the capacitor S1, the kept S closed and we close S2. The discharging time constant is T2. So R1, R2 and the capacitor and the EMF of the voltage. So what are the value for the T1 and T2? So the charging and discharging of the capacitor in an RC circuit, resistance capacitance circuit is calculated by this simple formula. Just multiply by the resistance and capacitance. This is the tau constant, which is the time required to charge or discharge. So for charging T1, this is charging. So this is T1, which is R1.
Victor,
Yeah,
RC is included in the final? I don't
sorry,
think so. RC circuit, I think they excluded from the final.
they excluded.
And they
We don't
deleted this
study it.
part.
Yeah,
Are you sure about it?
yeah, the syllabus is not included.
Okay, so okay,
We did
So
not
now,
study it, doctor.
okay. So just okay. Now next move to magnetism. Now we are moving to the last section, which is magnetism. So how magnetic field is produced? So when a current flow across any conductor or a wire, so it produces a magnetic field around it. And how do we calculate the magnetic field? Is by Ampere's law, which is mu naught I enclosed. So if you remember your Gauss law would be like this. It is for the surface dA over here, and over here there is there is a current enclosed, and over there is the charge enclosed, and over here is a loop integral because magnetic field loop around the circle. So it's circular path. So we calculate this loop. For a circular path, this magnetic field will be closed loop integral. So this dl would be only 2 pi r, which is the circumference of the circle. So b will be mu naught I over 2 pi r for this simple calculations. Okay, so how do we find the direction of the magnetic field? Is your right hand rule. That's very important. So your thumb will give the direction of the current always. Your curled finger, curl in the finger, curl your finger in the direction of the magnetic field. So curl fingers will give magnetic field, and your palm, always your palm will give you the force. Okay. So if you see this diagram, so the particle is entering in this like this part, and the magnetic field is in this direction. Okay, so in the figure below, a negatively charged particle enters uniform magnetic field perpendicular to the plane of the page. What is the direction of the magnetic field? So if you if you apply your right hand rule, so this direction will be your thumb, and then you curl your fingers like this, like this, like this. Okay, so it will be affected towards the left. Okay, so apply your right hand rule. This is the your entry of the charge particle, which is I. Then you curl your finger to the direction of the magnetic field, and your palm will give you the force. The force is inward, and the magnetic field is towards the left. Now the next question is, a horizontal power line is having a length and carries a current, which is this, as shown in the figure. The earth's magnetic field B is given. The location is directed towards this center at the angle to the north is 65 degree below the power line. Find F and the direction of the magnetic force. So this is the direction, and this is the direction of the current magnetic field.
Doctor,
Yeah,
for question 21, it's wrong.
sorry.
It's meant to be, for question 21, it's meant to be outward, not to the left.
Yeah, it would be outward. You're talking about, yeah, we are magnetic field. Yeah, sorry, I was thinking about the force. So yeah, yeah, yeah. The magnetic field is outward in that case. Okay. Okay. So next, if we move to the question 22. So find the magnitude of the force. So what is given? Length, the current, the angle. So the force is nothing but I L B sine of theta. So when we substitute all the values you are given in this question, you will get 5.78 Newton. Now the direction. How to find the direction? Just apply your right hand rule. So we have inward into the page and out of the page. So apply your right hand rule if you have the direction. So your palm will be your will be your the force. So in that case, what will be the direction? Inward or outward? So if you remember the cork rule, so this is the direction for into the
into.
page, into the page, and this is the out of the page. So the force will be into the page. Okay, one important rule remember as well. So if the current is going like this, clockwise or anti-clockwise, okay, clockwise or anti-clockwise, always remember the screw rule. So what is screw rule? So if you tight the screw, okay, it will go inside. Okay, so if you are moving it clockwise, it go inside, which means the magnetic field is inside. And if you move it outside or it rotate it outside like this, it will go out. So magnetic field will be outward. So remember this rule if you have a circulating current. And here the next question is a circulating current is coming. So in an electric motor, the circular coil have 100 tons with a radius this rotate between the poles of the magnet. When the current through the coil is 75 milliampere, the maximum torque that the motor can be deliver will be this. What is the magnitude of B? So when you place a coil or a circular loop into a magnetic field, it experiences a torque. And this torque is nothing but INAB sine of theta. For the maximum torque to be happen, this sine of theta will be 90 degree. So it will be 1. So the torque maximum will be NIAB. So N is a number of turns, I is the current, A is the area of this circle. So if you have a circle, so the area is pi r squared always. So this is pi r squared. So we want to find B, which is tau maximum divided by NIA, and you will get A pi r square. And you have the radius r, you have the current I, and you have the torque, and you have the number of turns. So just substitute the value and you will get your answer, which is 0.212 10 to the 3 Tesla. So So B is 0.212. So millitesla is, you have to multiply it with the 1000. So it will become 212 millitesla. So now if you see this, the current is in the clockwise direction, anti-clockwise direction. The magnetic field will be outward. So the torque will be in that case will be counterclockwise. Okay, so now question number 24.
Doctor, it's clockwise, not counterclockwise.
So the magnetic field is in this direction. So it moves like this. Did you get that?
دكتور clockwise correct.
Hmm?
It's clockwise correct.
This is we're talking about the
Counterclockwise.
torque.
Yeah,
Torque,
counterclockwise.
torque. We are talking about the torque. The force is
No.
experienced, not the magnetic field. It's about the torque we are talking about.
Okay, yes, counterclockwise.
Okay.
I get it.
Okay. So now the next question, move it quickly now. An electron moves in a circle with a radius this and velocity this, a uniform magnetic field. The magnetic field is into the page, which is represented by this cross. What is the magnetic field? So when an electron enters into the magnetic field, it moves in a circular path, which means it requires a centripetal force, which is Fc is equals to mv square over r, and r is the radius. So what is the magnetic force? Is q v cross b, which is qvb sine of theta, and theta will be maximum if they are perpendicular to each other. So it will be 90. So theta will be 90 degree. So your magnetic force will be qvb, and your centripetal force will be mv square over r. So when they both are equal, so it will be qvb is equals to mv square over r. So this is the charge of the electron. Q is the charge of the electron, E, and this is the mass of the electron. So one velocity will be cancelled out, and the magnetic field will be B is m v over qr, and this is the charge of the electron and the charge mass of the electron and the charge of the electron, and we'll substitute the value. We will get 6.75 to 110 to the -4 Tesla. So yeah, this is the answer. So this is a lengthy question as well. I will share the file with you with the solution. So just remember that these two currents are opposite. So you have to calculate the electric field. So when you substitute the value over here, so this will become under root 2a, if because it's a right angle triangle. And I've told you the formula bu naught I over 2 pi r, and this is your r. And because they are anti-clockwise, or opposite to each other, so for this it will make an angle 225, and then you will get the magnetic field B1, and then will magnetic field B2, and then you will add the total magnetic field B, which is B1 plus B2, and for that you will get your magnetic field, which is 480 microtesla along the positive, along the negative axis, along the negative axis. In this direction is the magnetic field. Next question is simple enough. So the wire is bent in a circular loop. The current is in this direction. So if you are seeing from this, if you are seeing from this, the magnetic field is in this direction. And if you are seeing from this, the current is in this direction. So magnetic field also in this direction. So both A and B is moving along the negative x-axis. For this question, you need to write the force per unit length, which is the Biot-Savart law. So first you will calculate the force 2, 1 and then 2, 3, and then you will add F21 plus F23, the total force, and you will get 52.0 micronewton. And the direction will be, in that case, upward. Next is the question, which is also just a concept question. So by applying the Ampere's law, B dot ds, or closed loop integral, is mu naught I enclosed. So if you see this, I enclosed is this and this are opposite. So you left with this current. So this is the answer. So next question is also related to Ampere's law. So B dot ds is equals to mu naught I enclosed. So you have two situations. One is to have to calculate this, and one is to calculate the current for this. So current enclosed will be the current and the difference, or the ratio of the area, which is nothing but pi r square and pi a square, because they have the difference radius. So the magnetic field, which is 2 pi r for closed loop, is equals to mu naught I r square and a squared. So the magnetic field will be 0.01275 Tesla, and it will be 1.28 millitesla. 1.28 millitesla. And the last question, which is also an easy question, this is a solenoid. And magnetic field for a solenoid is mu naught Ni and mu naught N over Li. So you have number of turns N, current I, L 75. So when you substitute the value, 16.3 millitesla will be your answer. So that's all for today. I will try to upload the video, and